Hello, DiplomaEdge students, and welcome to the last part of Reactivity 2. And we're going to start talking about equilibrium. In this video, we're going to cover section 2.3.1, which introduces dynamic equilibrium. And we're going to see what does it mean for a reaction to be in equilibrium. And the first thing that we're going to talk about is the definition of equilibrium. And for equilibrium to happen in a chemical reaction, the first thing that we need is a closed system. We're going to define what a closed system is later. But there are reactions that actually can happen in the two directions at the same time, from the reactants to the products and from the products back to the reactants. So if we have a chemical reaction, for example, a simple one here that starts with a reactant A, at the start of the reaction, we only have A. We only have the reactants, maximum concentration. As the reaction is proceeding, we start getting B, which is the product. And the rate of the reaction from A to B in direction to the product is very, very high. The reason is, well, because we don't have any B to start with. We just have reactant, the product still to be formed. But because this reaction can happen in both directions, as the product starts to be formed, some of that product is going to start becoming back the reactant. And at the start, the speed of this backwards reaction is going to be slow. But as the process is happening, the concentration of the reactants is going down and the concentration of the products is going to start going up. And we know that concentration is one of those factors that affect the rate of a reaction. So there is a moment as the forward reaction is slowing down and the backwards reaction is speeding up, there is going to be a moment where the two rates of reaction are exactly the same. And in that moment, we have reached the equilibrium. It's that moment in a chemical reaction where the forward rate is exactly identical to the backwards rate. So meaning that the speed of the forward process is the same as the speed of the backwards process. And in that moment, concentrations remain constant. So from the outside, you might think that the reaction has stopped because you don't see a change in concentration in reactants and products. But the reality is that this is a dynamic process. And by dynamic, we mean that even when the concentrations are not changing, the process is still going because the forward and the backward reaction are still happening, but with the same rate, so there is no change in concentration. As an example of a dynamic process could be a guy in the gym running in a treadmill. The guy is definitely moving, but the guy is not going nowhere because the treadmill is going in one direction and the guy is running in the opposite direction. Because the speed in the forward direction of the guy running is the same as the speed of the treadmill going in the backwards direction. From an outside point of view, if you look at the guy is not moving, but you know that the guy is running and you know that the treadmill is actually functioning. This is a process which is in dynamic equilibrium. In a chemical reaction, happens exactly the same. And for you to understand what a closed system is, because it's a requirement, logically, a closed system is a system where matter cannot enter or leave the system. So you start with the same amount of matter and you finish with the same amount of matter. Energy can get in and out, but the matter cannot. And what this means is that you start with an initial concentration, you finish with a final concentration, and what you have in the system is what you have in the system. You're not adding anything to the system. And equilibrium needs a closed system. When the equilibrium is reached, it has to be in a closed system, because if you're adding or removing reactants, suddenly the system is not closed anymore and the equilibrium is not going to be reached. And if we look at the characteristics of the equilibrium, you are going to see that there are two things that are important in equilibrium. The first thing is regarding the rate. The rate of the two reactions at equilibrium is exactly the same. So the forward and the reverse reaction have exactly the same rate, as you can see in this first graph. In this first graph, I have in the x-axis the time, so the reaction is proceeding in one direction, and in the y-axis I have the rate, and I have two lines. I have a line for the reactants. I'm going to see what happens to the rate of the reaction forward, and what I see is that it starts very fast and gradually gets slower until it plateaus. It plateaus because the rate is not changing. And if I look at the products, which in this case is with the dashed line, the rate of the reverse reaction is slow. It's zero at the start when there is no product. There is slow, but is increasing in rate until it reaches a maximum where the line actually also plateaus. And in that moment where the reaction forward and the reverse reaction have exactly the same rate is where the equilibrium has happened. And another characteristic of the equilibrium is that the concentrations do not change. You don't see any observable changes in terms of reactants and products in the equilibrium. The second graph illustrates this. In the second graph, it's exactly the same thing as the first one, but instead of the y being the rate, now the y is the concentrations. And I have two lines, blue and red. Red, concentration of the reactants, starts high, starts going down, plateaus. And blue, concentration of the products, starts in zero, because you don't have any product at the start, starts going up, and then plateaus again, gets flat. When the two concentrations are not changing, when they are horizontal, in that moment is where the equilibrium has been reached, because there is not an observable change in the concentrations of reactants and products. And the reason is, as you have in the same graph, because the rates are exactly the same. And this is pretty much it for this first video on equilibrium. We have defined dynamic equilibrium as a moment in a chemical reaction where the forward and reverse reactions occur with the same rate. We have seen that this has to happen in a closed system where matter is not exchanged in and out of the system. We have seen that the concentrations at equilibrium remain constant, so there is no change. You cannot observe any changes. And we have seen that the system is dynamic, meaning that even when the concentrations don't change, it's not because the process has stopped. The process continues in both directions with the same rate, with the same speed. So it's a dynamic process. It's constantly moving, but you cannot see that it's moving because what you're measuring is reactants and products. And in the next lesson, we're going to continue with equilibrium, and we're going to talk about the equilibrium constant and how do we interpret the equilibrium constant. I'll see you there in Diploma Edge.